Hello, sir. Sorry for canceling the meeting. Actually, one of my family member want me to take them somewhere, and it was made in a hurry, and I'll have to be there. So yeah, I'm sorry, but basically I'm making this video. So whatever I wanted to discuss, I'll just say in this video, and you can just comment on this in the email, and if a discussion is required, then we can meet whenever you are free next. So but after a couple of days, of course. So I'll be busy for 2 3 more days probably. So uh, yeah, I have been reading Borgs, and uh, I there are a couple of things that I am confused about, but they are mostly steps in calculation. I have understood the idea of the proof of result that we wanted. Uh, to be honest, it was quite accessible. I expected it to be much more mathematical and something I'll need to learn more things to read it, but actually it was quite accessible. So I have got the idea of proof. Our next goal is to write that proof for number partitioning problem with arbitrary targets, but there is a slight problem with that which I'll come to in the end of this video. Uh, First, what I wanted to discuss is the skepticisms that I raised about this approach in the last meeting, and I think there was some confusion about it. So I'll state it clearly now, and please comment on it. What do you think about this? So yeah, let's just start. So let's first review what our argument was. So let's start with a neural network, and what we were saying in Penzias's construction is that to each weight of this neural network, let's say this is a target network which we want to approximate by some bigger network. This is a given network, and what we did was is we took a weight of this network, let's say this one, the red one, and we insert a gadget, this gadget here, uh, whole layer, a small layer which connects this neuron to this neuron, this one, and we do this with every other weight in this network. So let me do another one. So take this one and insert a gadget here, and I'm not showing all, but let's assume that this procedure is done for all network, all the weights of this target network. So we have a much bigger but much sparser network, and now what we want to do is we want to prune this network in such a way that each gadget that is assigned to a weight in the target network approximates, or okay, we are not talking about approximation, so we are talking exactly. So let's use the word replicate instead of approximate. So we want to prune in such a way that each gadget replicates the its corresponding given weight in the target network. And what we said then is that pruning each pruning each gadget in this bigger network is equivalent to solving a number partitioning problem. And what we derived from the Martin's paper is a condition on when the number partitioning problem can be solved, basically. So when it has an exponential number of solutions, and when the solution number of solutions drop to 0, we have a condition for that. And uh, this was the condition which is written given on the screen right now. Here delta is the precision of the neurons, n is the number of neurons in each gadget, and z is the target of the number partitioning problem, the corresponding number partitioning problem of each gadget. And uh, a couple of things to note here is that each of these number partitioning problems, one corresponding to each weight in the target network, is independent of each other. So each gadget gives one number partitioning problem, and what we want is that each of them is solvable. So basically each gadget should approximate the weight that it is assigned to approximate, or as replicate in other words. And To do that, we want this condition, which we have derived using a non-rigorous argument, to hold for each of the gadgets. Another important thing is that this uh, uh, we want to get to that weight exactly. So we are not talking about uh, getting let's say in an epsilon neighborhood of the target weight. We want it this condition guarantees that it will be once it is satisfied, we'll be able to exactly replicate the weight. And another thing is that this is a binary condition, so it either it will be satisfied or not, and there is no in between. So uh, so these basically now I would like to speak about how these facts make our approach extremely different from what let's say Pensia is doing, for example. So, and this is my first criticism, my first skepticism, as to say, of this approach, is that we cannot make any estimates on this. So, the argument is this: well, we want this condition to be satisfied, and we want it to be satisfied for all gadgets. But you see that for given delta A and for given n, this condition will automatically be satisfied for all gadgets if it is satisfied for the gadget with maximum z, because log is monotonically increasing. So, and we want the left side to be less, so z. So if it is satisfied for max of z, then it is satisfied for all z's. And only thing that one gadget has different from another is the z, the target, because the weights in the target network are different from each other. So yeah, so basically this condition only depends on the maximum of the targets. Well, not exactly the targets, because as we have seen before, that pruning procedure is equivalent to a subset sum problem, and then we are writing it as a number partitioning problem. So target is not exactly the weight, but something related to the weight, but that's just a detail. So yeah, I was saying that it only depends on maximum of this z value. And uh, what problem does it makes is that Pensia was using Lueker's result, so which states that what with what probability a subset sum problem can be solved, whereas here we are saying that moment the condition is not satisfied even for one of those uh, number partitioning problems, we cannot replicate. And we are not talking about epsilon approximations, we are anyway talking about exactly getting to that weight. So what Pensia did is that for all these gadgets, pruning them is an independent event, and you can calculate for independent events what is the probability of let's say 10 independent events happening together, for example. But here, the moment you cannot approximate one, you are gone. Also, apart from this point, it seems weird to me to even like talk about this exactness, because in the whole problem of strong lottery ticket hypothesis is that we have a function, a target function, and we want to get epsilon close to it. And here we are saying that we have a condition that a very arbitrary condition which only depends on, let's say, one weight of the target, and uh, once the condition is satisfied, yes, you are there, but if not, then we have absolutely no idea. So um, it's a bit questionable. But yeah, this is a problem that we cannot make any estimates um, with this approach. Second problem was the problem of applying this result to other architectures. So as you see that as I mentioned in the previous slide only, that this condition will only eventually depend on the weight which provides the maximum target to the okay the gadget which provides the maximum target. And So let's say you want to apply this procedure to any, like let's say other architecture, or let's say you want to do other kind of pruning, let's say structured pruning. Well, you would go about it the same way. You will basically make some other kind of gadgets, make some other kind of construction to and then you will prune that construction, and that pruning will be equivalent to some number partitioning problem. And again, eventually you will have many independent number partitioning problems, and what we would be eventually able to say is that uh, whenever R given condition does not holds for maximum target, it does not holds in general. So doing any other kind of thing will not change the condition that we are proposing, because it only depends on uh, one weight in the target network. So yeah, that is what I wanted to say, that we cannot do any other architectures because it will, or any other kind of pruning, because it will eventually lead to the same thing. And the third problem, this is something that I did not talked about last time, but I think this is a major problem. This is much more highlighted in Borgs. After reading Borgs, I pay much more attention to this, and uh, yeah, I think this one needs to be addressed first of all. So basically, the problem is that we have been saying all along that we have a number partitioning problem and we have a condition, and once the condition is satisfied, there exists an exponential number of solutions and to the problem, and if not, then the number of solutions tend to 0 in the asymptotic limit, which is like when your given set is infinitely large. So but if you think about it, if you have a set and the sum of elements of this set is odd, then you cannot make perfect partitions with it. Let's say we are dealing with number partitioning problem with 0 target. So basically you have to partition it such that the sum of two partitions is equal. Well, you cannot partition an odd number in two equal parts. That's the definition of odd numbers. So you cannot do it. So the way Borgs get over this is he defines perfect partition in such a way that if sum of your set is odd, then a perfect partition is defined as two disjoint is like, okay, let me say this properly. If the sum of your given set is odd, then a perfect partition is defined as when the difference of sums of this set is 1. So the discrepancy is 1. We have just seen that it cannot be 0. So we define such so when the sum is odd, we define it such that the discrepancy is 1. And then what Borgs does is he calculates the expectation of when the perfect partition exists separately for the events when the sum of set is odd and sum of your given set is even. And then he goes about proving the results separately for these two cases. So the problem that this fact creates is that we are talking about approximating the target weight exactly, but we know that in general it can never be approximated. What if the sum of the number partitioning problem that we have got, the sum of that corresponding set is odd? So then you can say that, well, we are not dealing with integers, we are dealing with floating point numbers. So we have divided our whole set by a, let's say, a huge number, and so it does not matter whether the discrepancy is 0 or 1, because the difference between equivalent 0 and 1 is very small. 1 here is, let's say, 0.0000001. But my skepticism about it is this, that the moment we say this, now we come in the regime of epsilon approximations and we are no longer talking exactly. So then someone would say that even if let's say the sum of your set is even, and your condition says that the perfect partitions do not exist, perfect partition does not exist, you can still have an epsilon approximation very close to it. So like how are you segregating these two things? So this is a big problem that uh, I'm extremely confused about, and we need to address this. So please comment on this. And uh, another thing is that we are yet to write uh, Borg's proof for an arbitrary target. So we just saw that a zero target creates this special case that when the sum of set is odd, then perfect partition does not exist. Uh, it is a question that what an arbitrary target would do. So like, will it create more edge cases that needs to be dealt separately? That is something that I am finding a bit hard to think, and that is something that I would also request you to give your comments on. Yeah, so that's it.